Welcome back everyone to the online classes of DPS Siliguri. This is the last lecture for class 12 and we are doing solution chapter. If you have followed the previous lectures, we were doing colligative properties. We covered all the colligative properties, that is relative lowering of vapor pressure, elevation in boiling point, depression in freezing point and osmotic pressure. I derived the relationship of molar mass of osmotic pressure yesterday. The equation, the Van der factor equation for osmotic pressure was pi is equal to CRT. This is what we have learned yesterday. And we also got the relationship for determination of molar mass of solute from this relation. That is where we stopped yesterday. Today, we'll first solve a numerical on osmotic pressure. Okay, I've written the question on the board. Let's see how can we solve it. Let's read the question. 200 centimeter cube of an aqueous solution of a protein contains 1.26 gram of protein. The osmotic pressure of such a solution at 300 Kelvin is found to be 2.57 into 10 to the power minus 3 bar. Calculate the molar mass of the protein. This is a direct question. Let's write the given first. Given 200 centimeter cube. So this is the volume, 200 centimeter cube. Immediately we'll convert it into liters. So 200 centimeter cube will be 0.2 liters. Of an aqueous solution of a protein contains 1.26 gram of protein. This is our given mass, that means of the solute WB, 1.26 gram. The osmotic pressure of such a solution at 300 Kelvin, temperature is 300 Kelvin, there is no need to convert, is found to be 2.57 into 10 to the power minus 3 bar. Osmotic pressure, we know it is given by pi, so it becomes 2.57 into 10 to the power minus 3 bar. Calculate the molar mass of the protein. Okay, now we know that from the Van der factor equation, pi is equal to CRT. Now, C is the molar concentration, that is number of moles by volume into RT. Now, number of moles is given mass by molar mass, RT by V. We have been asked to find this. So, we'll bring MB on the left hand side. WB is 1.26, R is 0.083, temperature is 300, okay, pi is 2.57 into 10 raised to minus 3 and volume is 0.2. Done? If you solve this, you should get 61039 gram per mole. That is the molar mass of the protein. Okay? So, in this manner, you have to first write the given, then derive it from the relation. Okay? Accordingly, whatever they have asked in the question. So, with this, I have solved numericals for all types of colligative properties. And with this, we will stop our discussion of colligative properties. Now, we will discuss a little bit of application-based questions which are based on osmosis and osmotic pressure. Okay? Okay. When we talk about osmosis, there are some related terms that come with that. So those are isotonic solutions, then we have hypertonic solutions, and we have hypertonic solutions. Okay. Now, what are isotonic solutions? Solutions which have the same osmotic pressure at the same temperature are called isotonic solutions. That means they should have the same molar concentration. Those are called isotonic solutions. Hypertonic and hypotonic. Let me choose an example to explain this. Suppose I have 1 molar solution of urea and 0.05 molar solution of sucrose. Okay? Now, 1 molar solution of urea will be hypertonic. That means it has greater osmotic pressure compared to this. So this will be hypertonic compared to 0.05 molar sucrose solution. And since here the osmotic pressure is less or the concentration is less, this becomes your hypotonic. This becomes the hypotonic solution compared to 1 molar solution of urea. Most of you have learned this, those who have biology, you have much more clear idea about this kind of solutions. So, one interesting fact why I want to discuss about isotonic, hypertonic and hypotonic solutions is because this is something that is applied in the field of medicine. We all know that the red blood cells, in our body have some kind of fluid in them. Now, the fluid that is present in the red blood cells is isotonic with 0.91% mass by volume solution of sodium chloride, that is saline water. Okay, it is isotonic with 0.91% mass by volume solution of sodium chloride, which means if you take this solution and place the red blood cells here, the red blood cells will neither shrink nor will they swell. So this is the isotonic, same concentration. This is the reason why when you want to inject some medicines, this saline water solution is taken as the solvent or as the base, and it can be injected intravenously. Next, if you take a solution whose concentration is less, that means below 0.91%, that means here this is hypotonic. Concentration is below 0.91%, and you place the red blood cells. What will happen? Water will flow into the cells and the cells will swell and they might burst. At the same time, if you take a hypertonic solution, that means concentration is greater than 0.91%, water will flow out of the cells, of the red blood cells, and the cells will shrink or they might collapse. So this phenomena or this processes that is happening plays a very important role in our life, day-to-day life. Why? Now, people with very high blood pressure, you must have observed that doctors tell them that they should not intake too much of salt in their diet. Why is that so? That is because when we take too much of salt in our diet, we tend to retain more water in our body and the osmotic pressure increases. The more salt you consume, the osmotic pressure increases. This causes a pressure in the cells or in the tissues, and water gets stored in the intracellular spaces, and this leads to a puffiness. Okay, this is your puffiness and a kind of swelling. This swelling or puffiness due to retention of water in the body is known as edema. Okay, this medical condition is known as edema. You have to learn about edema. Just in brief, Okay, why like application-based questions are asked. Why should a person with high blood pressure should not take high salt in their diet? So you should explain using a high concentration of NaCl having the leads to greater osmotic pressure, and that will lead to retention of water in the intracellular spaces and tissues. This leads to puffiness, and this condition is known as edema. Okay. All right. So that was about what is happening within our system. Now, osmosis also has some very good applications in our daily life. Like whenever we bring flowers to our homes, we directly put it in a flower vase in water. We do that because we know if we don't do that, the flowers will wilt due to loss of moisture. Okay, the flowers will lose moisture and will wilt. Similarly, when you bring vegetables from the market, you put it in the freezer so that the moisture is intact. If you leave, suppose I take an example of a carrot. If you leave a carrot outside, it will become limp. You take the same carrot and put it in water, it will become turgid after some time. So this is again due to flow of solvent molecules due to osmosis. Another question that was asked in this year class 12 paper was, why is salting of meat done, or how does it prevent the meat from getting how does it preserve the meat? Now when you add salt to meat, what happens is the water from the meat flows out. This actually prevents the bacterial growth in the meat, and this will help you to prevent your meat for a longer period of time. Same thing happens when we are making pickles. We either add too much of salt or we add sugar. Okay, so these are the applications of osmosis in our daily life. Okay. Now my discussion about osmosis does not stop here. The last topic is reverse osmosis. Reverse osmosis. Now what is reverse osmosis? Osmosis is flow of solvent molecules from a region of low concentration of solute to high concentration of solute. So reverse osmosis will be definitely the opposite. That means from high concentration of solute to low concentration of solute. Now I'll explain this with the help of a figure. Okay. So I have this two vessels which are again separated by a semi-permeable membrane, SPM. I'll take seawater this side and fresh water this side. Okay. Now, if you want that your osmosis should take place in a reverse direction, we have to apply a pressure on the solution side. That means I need to apply a pressure here. And how much pressure? We have to apply a pressure which is greater than the osmotic pressure. We must remember that on application of osmotic pressure, the flow of solvent molecules will just stop. But if we apply a pressure which is greater than the osmotic pressure, the solvent molecules will start flowing in the reverse direction. Okay. Now, you see I've taken seawater and fresh water. So if we apply a pressure which is greater than the osmotic pressure, the water molecules will flow into the fresh water container. Okay. This is a very, very important application in our daily life, because nowadays most of the countries are meeting their drinking water requirement by this method. This is known as desalination of seawater. Desalination of seawater. Many countries have made plants, desalination water plants, so that they can purify the seawater and convert it into fresh water. Now, one thing that we must remember is the semi-permeable membrane that we choose for desalination, for reverse osmosis, is a special type of semi-permeable membrane. One example I'll give you is cellulose acetate. Okay, cellulose acetate, ACETATE, cellulose acetate, which is supported over a suitable, support. Now, cellulose acetate is chosen, and cellulose acetate, it allows only the water molecules to pass, but it does not allow any other ions of, say, water to pass. Okay, so these are the information that you should remember. This is also a question, they might give you the figure, ask you questions from the figure. They might ask you directly that what is reverse osmosis and explain with the help of an example. Okay, so this is reverse osmosis. Done. So we are done with osmosis now. After this, we have to discuss about, okay, so the next topic is abnormal molar mass of electrolytic solutions. Now, the very term abnormal molar mass, will strike you. What is abnormal molar mass? Till now, you have been doing only molar masses of solutes, right? Whatever colligative property we studied, for those colligative properties, we have derived a relationship. Like, for example, I'll say Mb is equal to Kf into Wb into 1000 divided by delta Tf into Wa. This kind of relations we have used for finding molar mass of solutes. Now, we must remember that these relationships, the values that we get from these relations, are basically correct when our solution is very, very dilute. When our solution is very dilute. Now, why dilute? What happens if our solution is concentrated? If our solution is concentrated, the solute will start interacting with the solvent. If this happens, the solute will start interacting with the solvent. And if this happens, you know what? The colligative properties will not depend only on the number of solute particles, but it will also start depending on the nature. It will also start depending on the nature of the solute particles. So in that case, the molar masses that you get are not correct. Alright? So next, so the first criteria is to get correct molar masses, your solution should be dilute. Second, your solute should not dissociate or associate in solution. Your solute should not dissociate or associate in solution. Now, when does this happen? All the colligative properties that we have studied till now, the molar masses that we have obtained, the relationships of molar masses that we have obtained are for non-electrolytes. Okay? Now, you have studied about electrolytes and non-electrolytes in class 11. What are electrolytes and non-electrolytes? Electrolytes are those which will dissociate or ionize in solution. And non-electrolytes are those which remain as such. They do not dissociate, they do not break down into their constituent ions, nor do they combine together to give another molecule, they do not combine also. So those are non-electrolytes. So whatever we have done till now are basically for non-electrolytes. Now what will happen if we choose an electrolyte? Okay, let's see. So two criteria is solution should be dilute and solute should not dissociate or associate in solution. Let's see what happens if our solute associates. Number 1, association of solute particles. Association of solute particles. Okay, to explain this, I'll choose an example. Okay, this normally happens in non-polar solvents. This normally happens in non-polar solvents like benzene. Okay, you have benzene, you have carbon tetrachloride. These are non-polar solvents. I want to take an example of acetic acid, that is CH3COOH in benzene. Now what happens when you add acetic acid in benzene? It forms a dimer. That means two molecules of acetic acid combine together to form a single unit, or it combines together to form a single molecule. Now how does this happen in solution? Let's see. This basically happens due to formation of hydrogen bonding. Okay, this is one molecule of acetic acid and this is the other one, O and H. So dot and CH3. So two molecules of acetic acid combine together to form a dimer. Clear? Now if this happens, the number of molecules in the solution will decrease. Our number of molecules decreases. That means your colligative property decreases. Whichever colligative property you take decreases. You can also understand this with the help of the relation that we have just taken. Okay, so I'll write the relationship again. Delta TF is equal to KF into WB into 1000 divided by MB into WA. See here, initially acetic acid, before going into the solution, its molar mass or molecular mass is 60. After going into the solution, it has been found that it doubles. It comes to 120. Okay, it comes to 120. So that means your MB is increasing, and molecular mass, molar mass and colligative property are inversely proportional, as we can see from the relation. So if this increases, colligative property will decrease. I hope this is understood. You can see I have explained this using two criteria. That means due to association, number of molecules decreases. If number of molecules decreases, colligative property will decrease. Also, due to association, molar mass increases, and molar mass and colligative property are inversely proportional, so colligative property also decreases. So in this case, whatever molar mass you get will be higher. Due to association, molar masses will be higher than the actual molar mass of the solute. Clear? So that is about association. Let's talk about dissociation. Dissociation of solute particles. Dissociation of solute particles. This is basically for electrolytes like acids, bases and salts. We know that acids, they ionize in solution, and salts also, they will dissociate. So this is for those kind of solutes. For example, I'll choose KCl. You all know that if KCl is added to water, it will dissociate into K++ Cl-. Now, in this case, if you prepare a solution, if you start with 1 mole KCl, okay, 1 mole of KCl, you are expected to get 1 mole of K+ ions and 1 mole of Cl- ions. That means the number of particles after you have prepared the solution has increased. If particles increases, colligative property will. Suppose I am taking temperature near freezing point, colligative property will increase. Also, the molar mass of KCl is 74.5 gram. After calculation, or after preparing the solution and doing the calculation, it has been found that it comes to 37.25 gram. Okay, so again the same relation, delta TF is equal to KF into WB into 1000 divided by MB into WA. If this decreases, this will increase. That is what is the relation, inversely proportional. So dissociation of solute particles, if it dissociates, number of particles will increase, molar mass will decrease, and colligative property will increase. Okay, so you must remember these points in mind, because with this, we have to go ahead with the topic of abnormal molar mass. Now, up to what extent your solute undergoes dissociation or association in solution was explained by Van Hoff, and he gave a factor which is known as Van Hoff factor. Okay, Van Hoff factor, it is given by I. Now, what is Van Hoff factor I? I is equal to normal molar mass by observed or abnormal molar mass. Okay? So, normal molar mass is whatever is a theoretical value, and observed or abnormal molar mass is the value that you calculate after you have prepared the solution. Now, in case I is equal to 1, that means your solute has not undergone association nor has it undergone dissociation in solution. If I is less than 1, your solute has undergone association. Clear? If I is greater than 1, it has undergone dissociation. This you must remember. Okay? Now, this is about Van Hoff factor with molar mass and abnormal molar mass. Now, we can extend the Van Hoff factor to colligative properties also. We know that molar masses and colligative properties are inversely proportional. So, I will be observed value of colligative property by normal value of colligative property. Okay? This is for colligative property, the formula for colligative property with Van Hoff factor. Now, whatever colligative properties we have learned, we can include the Van Hoff factor in those colligative properties. How? Relative lowering of vapor pressure was delta P by P naught is equal to mole fraction of solute. So this becomes I into mole fraction of solute. Delta TB, elevation of boiling point, was Kb into m. This becomes IKBm. Delta TF was Kf into m. This becomes IKFm. Last, pi was equal to CRT. This becomes ICRT. Now, all these formulas are extremely important for numericals. Okay, you might be asked to find the Van Hoff factor or any information, all the other informations might be given, and you might be asked to find the osmotic pressure also, depending on the question. So these formulas, I believe this is all these are there in the NCERT. So when you're preparing your notes, write them down. So this will help you to remember more. Okay, let's try to solve one numerator. Okay, I'll solve one numerator. Alright, so the numerical that we are going to discuss with using Van 't factor equation is the one that I've written on the board. Let's read the question. Calculate the boiling point of solution when 2 gram of sodium sulfate having molar mass 142 gram per mole was dissolved in 50 gram of water, assuming sodium sulfate undergoes complete ionization. Kb for water is given to you. Now, just a few minutes back, we have discussed that if your electrolyte undergoes association or dissociation, the relationship for colligative property is modified. Now, here it is given that calculate the boiling point of solution. So, I know that delta Tb has to be calculated. Now, we know that using Van 't factor, the relation is delta Tb is equal to I Kb m. Okay. Now, m is the molality, so delta Tb becomes I into Kb into Wb given mass, Wb into 1000 divided by molar mass into mass of solvent. Okay, so this is the relation. Now, let's find out what is there in the question, given in the question. Calculate the boiling point of solution when 2 gram of sodium sulfate, that is Wb is 2 grams. Molar mass of sodium sulfate, Mb is 142 grams, was dissolved in 50 gram of water. Wa is 50 grams. Assuming that sodium sulfate undergoes complete ionization. Okay, Kb is also given. So Kb is 0.52 Kelvin kg per mole. Okay, this is for 142 gram per mole. Now, Wb is there, Mb is there, Wa is there, Kb is there. We need to find out I. How do we find out I? If the information given is sodium sulfate undergoes complete ionization. So let's try that. How to represent the dissociation. Na2SO4 will give you 2 Na plus ions plus SO4 2 minus ions. Since we are getting 3 moles of particles after the electrolyte has undergone dissociation, so my I becomes 3. Okay? If instead of sodium sulfate, NaCl was given to us, we know that this will dissociate to give you Na plus Cl minus. So I will become 2 on complete dissociation. So the number of moles of ions that you get after dissociation, you need to count that and you get your value of I. Okay, so here we have calculated for sodium sulfate and I has come out to be 3. So we have got all the required information. Let's put it there. So delta Tb is equal to 3 into 0.52 into 2 into 1000 divided by Mb is 142, Wa is 50. If you calculate this, it should come to 0.439. Okay, now this is the difference. You need to find out the boiling point of the solution. Now the solution was prepared in water. So, boiling point of solution will be, we know that the boiling point of water is 373 Kelvin. We need to add this value, 439. So, it will be 373.439 Kelvin. Alright, so this is how we will use the information if it is mentioned about an electrolyte which undergoes association or dissociation. Okay. Now, there is an extension to Van 't factor. Okay, like how Van 't factor can be used to find out the extension, to find out the extent of dissociation or association of a solute. This is done with the help of a factor which is known. This is done with the help of degree of association or degree of dissociation. Let's see what is degree of association and degree of dissociation. Okay. Alright, so we have degree of association and degree of dissociation. Okay. Degree of association is given by alpha. It is equal to, the formula is number of moles of the substance that undergoes association, that is number of moles of the substance associated, divided by total number of moles of the substance taken. Alright? And this side, degree of dissociation, which is given by alpha, is equal to number of moles of the substance dissociated by total number of moles of the substance taken. Okay, so this is the formula for degree of association. Now, how is degree of association alpha related to Van't factor? Okay. Now, for association, alpha is given by, alpha is equal to I minus 1 by 1 by n minus 1. What is I? I is the Van't factor. The information for Van't factor, we know the formulas are normal molar mass by abnormal molar mass. You can also use, if the question is given in terms of colligative property, it will be observed colligative property by normal colligative property. So this is Van't factor. What is N here? I have given an example of acetic acid in benzene. CH3COOH in benzene undergoes association to form a dimer. So this is the dimer. That means two molecules of acetic acid has associated. So N becomes 2 here. That means the number of molecules which associate. You can check the other methods also, which is written in the book, but I prefer to choose alpha straight away with this relation. Okay, so similarly, alpha for dissociation is I minus 1 by n minus 1. That means for electrolytes like KCl, which will dissociate as K plus and Cl minus, the value of n will be 2. The value of n will be 2. Similarly, for potassium sulfate, K2SO4, which will dissociate as 2K plus SO4 2 minus, the value of n will be 3. So you can use these values and put it straight away in the formula after calculating the Van't factor. Using this formula, we'll solve one numerical. Okay? Okay, so the numerical related to degree of association I have chosen is this one. Let's read the question. 2 grams of benzoic acid, whose formula is C6H5COOH, dissolved in 25 grams of benzene, shows a depression in freezing point equal to 1.62 Kelvin. Molar depression constant for benzene is 4.9 Kelvin kg per mole. What is the percentage association of acid if it forms double molecules, that is dimer in solution? The percentage association, that means they have asked you to find alpha. Now association, just now we have got the formula that association, for association degree, the formula is alpha is equal to I minus 1 by n minus 1. Now n is there with us because it forms dimer, so n will become 2. I need to find out the Van't factor I. How to find out I? All the other information is there in the question. We will use that. Let's start. Okay. Now, if this benzoic acid formula is given here, we will find out that I is equal to normal molar mass by abnormal molar mass. So, depression is freezing point. So, delta Tf is equal to Kf into given mass into 1000 divided by molar mass into Wa. Now, Nb is equal to Kf's value is 4.9, Wb is 2 grams into 1000 divided by, we have delta Tf here, depression and freezing point is 1.62, Wa is 25. If you calculate this, you are supposed to get 241.98 gram per mole. So this is our observed molar mass. Now we know that from Van't factor relation, I is equal to normal molar mass by observed or abnormal molar mass. Okay. Now, what is the normal molar mass? We need to calculate C6H5COOH. So that is 6 into 12 for carbon plus 5 into 1 plus 12 again plus we have 2 atoms of oxygen, that is 32 plus 1. This will sum up to 122 gram per mole. So I becomes, normal is 122 divided by 241.98. This on calculation will come to 0.504. 0.504. So I is 0.504. Let's put this value in alpha now. Okay. So we have got everything that we require. So alpha was I minus 1 divided by 1 by n minus 1. So alpha is equal to 0.504 minus 1 by 2 minus 1. If you solve this, you will get alpha is equal to 0.992. That is, the degree of association is 99.2%. Okay? Alpha is 0.992, so in terms of percentage it will be 99.2%. Now what do you understand by this? It means that in the solution 99.2% of the molecules of benzoic acid has combined. That means 2 molecules have combined to form the dimer. There is not 100% association. There is 99.2% association of the solutes. So I have done association here, I have solved association. I have given you the formula for dissociation and I have given one numerical with dissociation in your worksheet. Okay, try solving that. It is also in the same manner. With this, I have completed almost every topic that is there in the chapter. You can follow the these lectures. At the same time, try preparing your own notes. If there is any extra information that you can take from the lectures, do that. Solve the NCERT numericals. There are plenty, I know, but go for the selective ones which have been repeated in exams. Solve those and complete this chapter as soon as possible so that you are updated. Because after 1 week or so, you are going to have another lecture where you are going to cover another chapter in chemistry. Okay, so with this, I'll say bye to you for now. Take care everyone and stay safe.